These super, yeah, okay, continue. So these new superconductors seem to be different from earlier simpler version of simple metal superconductors. And I wish to show you today how different they are. And so, yeah, so we will show you experimental results of mainly 3 different techniques, but mostly muon spin relaxation. This is a technique that Zurab and myself are using to study superconductivity of these new materials. And our results will be also connected to the results of neutron scattering, and most recent one of transient optical responses studied in Hamburg, Germany. And what I hope to show you is the phenomenology. This is to plot various experimental data and talk about their relationship and also their commonality, analogy. And I will show you analogy between all these superconductors and superfluid helium. And theoretically, we hope to show that most of these things can be understood by concept of Bose-Einstein condensation to BCS condensation crossover if your superconductivity is especially competing with the magnetic order. Okay, so unconventional superconductors we call is different from what is known as BCS superconductor. And BCS stands for Bardeen, Cooper, and Schrieffer, who got Nobel Prize for explaining superconductivity of simple metals like tin, aluminum, or indium. They are called BCS superconductor, and they got Nobel Prize in 1972, I think. So the superconductivity mechanism of these simple metals are kind of explained already and were understood. But those new materials show different behavior. And in my opinion, there are 4 characteristic different behaviors. The first one is that the superconducting transition temperature, TC, scales with the superfluid density. This I will show you soon. And this is what we discovered in 1989. And this is not what is expected in area simple metal BCS superconductors. The second difference is showing up in something called pseudo gap behavior. And this is measured at by nuclear magnetic resonance or angle resolved photo emission. This is also coming out around about 2 years after the discovery of high temperature cuprate systems. And the third difference shows up in vortex-like Néron's effect and diamagnetic susceptibility. These were noticed in year 2000 and afterwards. These actually are special property in the normal state above the transition temperature, and they are not expected in BCS superconductors. And finally, the most recently, people read by the group of Andrea Cavallari in Max Planck Institute of Hamburg discovered that if you shine light, laser light, on these unconventional superconductors, they can induce the behavior, something looking like superconductivity, but in a very short transient time scale. And this is we call photoexcitation. After photoexcitation, there's some transient phenomena with which shows very high apparent TC, transition temperature of nearly room temperature. And so these 4 behaviors are not expected in area simple metal superconductivity. So I would like to show this behavior as well as try to understand and propose a phenomenology based on the results of equilibrium or transient superfluid density and connect all these 4 phenomena if possible. Okay, but before that, let me spend about 5 minutes to explain this experimental technique that Zurab and myself are using. This is called muon spin relaxation or rotation. And this is to utilize radioactive particle positive muon for the study of magnetic or superconducting materials, something similar in principle to nuclear magnetic resonance. But we will show you how we do this. This has to have, we have to use or go to a strong accelerator facility to have radioactive unstable particle positive muon. So muon beam can be obtained in 4 different places in the world. So one is in Triumph Accelerator in Vancouver, Canada, which we have been using mostly, and I got PhD, for example, from the results of this facility. And another one is Paul Scherrer Institute. This is the strongest facility that Zurab is working in Zurich of Switzerland. And there's a slightly different type of facility in near London, in ISIS, Oxford. And there's another facility in, there's one other facility in Japan. Please assume that these facilities would generate very strong muon beam of spin porous muons. And this is, I'm showing this experimental setup. And actually muon beam comes through this pipe here. And then our experimental specimen is put into, this is a cryostat, so into this cryostat. And what we measure is radioactive particle arrival of muon and muon decay positrons by using the plastic scintillation counters. Okay, and you're also seeing that the magnetic field can be applied, parallel to this beam or perpendicular to the beam. And so this is very much like a very simple nuclear physics or particle physics experiment. Okay, so let me explain to you its principle. So muon spin is polarized parallel to its beam usually, and so these accelerators would give us 1 muon per every something like 10 microseconds, so on. And so we measure this is the shaded area is showing as the specimen. And so we stop this muon beam within the specimen. The specimen is actually something of the size of a coin. And the muon beam is stopped within about 0.1 millimeter from the surface. And muon will spend almost all its lifetime within the material, just sitting in some position of interstitial site in a crystal, and essentially looking at magnetic field from surroundings, and then decays. So what we do is to record the arrival of muon by this counter, which is called identification counter M. And then if we wait for about 2 microseconds, so average lifetime of positive muon is 2 microseconds, then the muon, which was sitting in the crystal, decays into 1 positron plus 2 neutrinos. And we detect the decay positron by using, in this case, for example, a counter in the forward direction and the counter in the backward direction. And we are measure the time interval of arrival of the muon and its positron decay. So, then we do 1 by 1. So we finish 1 decay event, and then we allow the second muon to come and measure the second decay event. And we accumulate about 1 million such decay event and make the histogram of how many events existed with what time, so lifetime, how much time muon is staying, and then how many positrons comes to the forward counter as well as to the backward counter. And so this is a typical nuclear physics lifetime measurement. And so what you will get is this exponentially decaying event time histogram. Okay, and however, the probability that positron is emitted, So one positron is emitted from one muon, but probability that positron is emitted has a correlation with muon spin. So if muon spin is keeping its polarization, then you have more positrons expected to come towards this forward direction as compared to the backward direction. Then what you will have in this histogram is that you will see this asymmetry of counting rate. Forward is more than the backward. On the other hand, by some mechanism of solid state physics or whatever reason, if the spin polarization is destroyed and lost, then this ratio of forward and backward counter would become 1-to-1 after normalizing this mechanical some solid angle factors. And so just by measuring the ratio of forward and backward counter, then we can record time evolution of muon spin, how this spin is, if it's stable in the material or if it's, polarization is decayed as a function of time. And this can be done nicely in zero field. Okay, you don't have to apply external magnetic field. This is radioactive decay of the particle carrying out the spin information by radioactive decay. And so we can get the spin information just in zero field. You can apply the field parallel to the spin direction, and then that is called longitudinal field, and that would create something comparable to the condition of nuclear magnetic resonance. But still, we do not have to have radioactive radio frequency RF field, and we can do very much similar thing by everything done by nuclear magnetic resonance without having radio frequency. And so this can be done in any material. We can implant muon to various different systems. So that is the advantage of this technique. But the method I would show you today requires applying this external magnetic field perpendicular to the spin direction. And then what happens is that this muon spin is precessing around this external magnetic field. And so you will see, if you have a counter here, for example, you will see the oscillation of muon spin as long as spin polarization is kept. And so by measuring from this oscillation, you can measure again how how long the spin polarization is maintained or if it's destroyed, and if the internal magnetic field in the material is same or different from the applied external magnetic field, and so on. So most of the studies of superconductivity that I will show you today is performed by this applying transverse external magnetic field. The field can be something like 1 kilogauss or maybe several hundred gauss up to maybe 1 Tesla. But fortunately, the things I will show you is not much strongly dependent on external field. And so just please remember that you apply field and we see this oscillation of muon spin around the field. Okay, so in the field of superconductivity, this is a plot of highest transition temperature as a function of year. And superconductivity was found in Mercury first in 1907 or something, 1911. Anyway, so early 19,000 years, and then people discovered slowly some materials with higher transition temperatures, but until this year 1986, the transition temperature was limited to something like 20 or 30 Kelvin, and then this gentleman in Switzerland discovered that some oxide material of copper oxygen compound shows superconductivity at very high temperature. And in 1986, it was discovered that such a system we call high TC cuplet systems has transition temperature goes up to something like 130 Kelvin. And the record at this moment is something like 160 or so, I think. So this high transition temperature is very much advantageous because you can get the superconducting state even with cooling of liquid nitrogen rather than liquid helium. So nitrogen is much less expensive, and so this allows various application of the superconductivity for high field magnet, like nuclear magnetic NMR imaging for medical uses, or levitation of a high-speed train by using superconductivity. And those applications getting much easier with this high transition temperature. But also together, after this year, almost all the researchers in the solid state physics have been working to explain why these new materials have such a high transition temperature. In fact, is the mechanism of their superconductivity. So we are, of course, one of them, and we started the studies of these new superconductors by using this mu-SR technique. Okay, so let me show you an example of the data that we take by using this mu-SR technique. This is for an example of the new superconductor, alkali potassium-3 doped carbon-60. So carbon-60 is something called buckyball system. This is again interesting soccer ball-like molecule of carbon, and that was a subject of Nobel Prize for, I think, 1991 or 2 or so on chemistry prize. And people soon found that the doping potassium or alkali metal would make this thing as a superconductor. And this material has a superconducting transition temperature of about 20 Kelvin. So this is a result showing what happens if you do this mu-SR experiment in this system. The upper figure is in the normal state. So this is not superconducting, this is just a metallic state at 24 Kelvin. And what we are showing is this muon spin oscillating around the applied external field of 22 kilogauss. And you see this oscillation is very much long-lived. And long-lived oscillation means that the frequency of this precession is the same for first muon as well as the last muon of 1 million muons. So all the muons would feel the same frequency, show same frequency because they are feeling the same magnetic field, which is essentially same as applied magnetic field of 2 kilogauss. But if you cool down this system into the superconducting state, what you will see is that this oscillation shows damping. And this damping is very much related to fundamental length scale of superconductivity and allows us to do some physics. But this damping can be usually fit with a Gaussian function. And we show you many of the data of what we call relaxation rate sigma, which is this Gaussian damping rate. But essentially, please remember every time that I show this relaxation rate, it is just the rate of this damping. So why do we see this damping in the superconducting state? And so if you apply like 2 kilogauss or such magnetic field to type 2 superconductor, this new superconductor is something called type 2 superconductor, then external magnetic field is accepted into the material, but by a special form of something called flux vortex lattice, or by each of the field would be accepted by making this flux vortex. And it is somehow in this core of the flux vortex, which is shown by this figure, the external field, the internal magnetic field of the material is the same as the applied external field. But the superconductivity has some property to expel the magnetic field. And this is doing that in a partial way, so that the region between this flux vortex core, for example, you see this in between this thing, the magnetic field is smaller than the applied magnetic field, okay? And what mu-SR is doing is that first muon may be stopping here. So he will precess with the magnetic field of this magnitude. The second muon may be stopped in the core, and then he will precess with this frequency proportional to this larger magnetic field. So we do millions of this event and add up together. So that means if there is a magnetic field inhomogeneity, that would contribute to cause this damping of the field precession. And so by measuring this damping, we can also determine how much the field is changing within different positions. Okay, and this flux vortex structure is something like a mesoscopic structure, because each of the flux vortex carries something called flux quanta. And so applying a given field immediately would allow us to estimate the size of this sort of ring size. And if we apply 1 kilogauss, this interval of adjacent flux is something like 1,000 angstroms. So this is a mesoscopic structure. But by doing muon experiment, we measure this damping rate sigma, and that is related to the inhomogeneity of this internal magnetic field. And that is also related to something called inverse of the penetration depth lambda. So this penetration depth lambda is the length scale that how the field would change within the superconducting system, you know, how this variation occurs. And in some mid-1920s or 30s or something, the researcher named Fritz London in UK found out with something called London equation that this 1 over the penetration depth square is related to the superconducting carrier density NS divided by the effective mass. And this is actually the effect that superconducting current flows around this vortex core and then screen the external magnetic field. And this NS over M star is a kind of measure of the superconducting current density. So by measuring this damping rate, we can measure this current density of the superconducting current, or this is something like a strength of the superconductivity. And this would tell us many things about how different this new superconductors are from the early superconductors and so on. So, okay. So this, actually, so this inhomogeneity of the field comes, as I mentioned, comes from something called Meissner effect, that is the property of the superconducting materials to expel the external magnetic field. And that is the origin of this magnetic levitation. This is a sumo wrestler with maybe a colleague of Tochinoshin named Tosanomi-san in Japan. He's sitting on this, actually there's a superconducting material in the cool down in this lower box. And he's sitting on a magnet. And magnet from magnetic field is expelled from the superconducting material in this white box, and that would make this levitation. And so this this triangular structure was predicted by the scientist named Abrikosov. He already passed away, but he was a Russian scientist, and he got Nobel Prize for predicting this structure in 2003. Okay. So anyway, so if you do this measurement, I hope you remember that we saw some damping, and this damping happens only below the superconducting state. So if you measure this damping rate as a function of temperature in this potassium 3C60, so the damping rate increases with when you enter the superconducting state or below the superconducting transition temperature, and show this kind of temperature dependence. And so because this damping rate is related to inverse of the penetration depth square, just measuring the damping rate immediately allows us to determine this important length scale, the penetration depth. And and for example, this data shows that at the lowest temperature, for example, this material, buckyball material has the penetration depth of about 5,000 angstroms. Okay, so this kind of measurement we can do in essentially if you have the sample specimen, any of various different superconductors. So I'm showing you here very early data of taken in high temperature cuprate superconductor about 2 years after the discovery. And by changing chemical composition, you can make various different high temperature superconductors having different transition temperatures. So this is a result of the material with transition temperature of about 70 Kelvin and 120 Kelvin. And we are seeing that this damping rate changes this way. And so immediately what you can say is that there are more this superfluid density, this carrier NS over M stuff, which we usually call superfluid density in the this higher TC material than the lower TC material. And you can also determine the penetration depths of each material accordingly. So soon after the discovery of this cuprate superconductors, we performed this experiment in many different specimens of copper oxide superconductors. The transition temperature of the copper oxide superconductors can be tuned or changed by changing the carrier density that is achieved by putting slightly different chemical composition. And then you will be able to see how TC temperature, how transition, we can measure the transition temperature and how it is related to the value of this damping rate at very low temperature, which is representing this horizontal axis is representing the superconducting carrier density divided by the mass. And these are each different specimens with slightly different chemical compositions. And in the high TC cuprate systems, it is known that initially you dope superconductors with charges, essentially superconducting charges, and the TC increases and then shows some saturation and then decreases. But this initial increase area is called underdoped region. And this data is showing that TC of this high TC cuprate superconductor, at least in this initial increase region with the doping, is related with nearly linear relationship with this superconducting carrier density divided by the mass. So I'm sorry, these points were here. I moved this slide and I forgot to move these points together back again. But so all these samples show sort of common ratio between TC and the superfluid density. So this means that TC is very strongly related to the superfluid density. And this is different from what you expect in the simple BCS, Badin-Cooper-Schrieffer simple metal superconductors. In the simple metal superconductors, the metals have something called Fermi-sphere, and superconductivity occurs as a result of electron-phonon coupling. But superconductivity occurs because there's something called energy gap made in the superconducting state around this Fermi sphere. And if you have energy gap, then there is no dissipation or scattering around. And that is the origin of this special quantum behavior called super something. And so that is a electric current without decay or without resistivity. This is all coming from the existence of energy gap. And in this BCS superconductor, energy gap, small energy gap or large energy gap is formed depending on the strength of electron-phonon interaction. And but what is known is that TC, the transition temperature, scales with this energy gap. And however, once a small energy gap is formed, then any small energy gap would make this system as superconducting. And what we are measuring, this number of carrier density divided by the mass, is not changed for, it's always this, all the carriers in the Fermi sphere that participate in the superconducting current or supercurrent or superfluid density. And so in the BCS superconductor, you can hypothetically think to make two different superconductors with a larger energy gap, with larger TC, and this red one with smaller energy gap with smaller TC. And those two superconductors would then still have the same superfluid density. So there is no direct dependence between the transition temperature and the superfluid density in the traditional BCS superconductors. So compared to this, our measurement, which we published in 1989, shows that these cupret superconductors have strong dependence between TC and the superfluid density, and so they are different from these simple BCS-like superconductors. This is the first probably signature that these two, these new superconductors are different from the area materials. Okay, then we continued because soon afterwards, many newer superconductors were discovered. Those saccaball, buckyball, carbon-60 superconductors are one of them, but also slightly later, there are many materials with iron arsenide superconductors. They were found, discovered, and interestingly, if you do this experiment by muons, what you see is that this TC is always almost nearly linearly related to this superfluid density. And there's something called overdoped region, but the data is also more or less nearly linearly related. And so this is telling us that this feature is not only confined to one particular system, but more generally, universally taking place in many different new type of superconductors. And to simply find out what is this implication, this measurement is just measuring the number density of carrier in the mass. So you can count how many carriers exist in the given area. And there is another important parameter in superconductivity called coherence length. That is the distance between two paired fermions, two paired charges. So superconductivity is the result of pairing of two fermions, two charge carriers into one boson. And but in the case of BCS superconductors, this coherence length, the distance of the pair is very large. So you have many, many pairs overlapping with a given, in a given region like this. But another different situation, similar but different situation, can be seen in superfluid helium. And superfluid helium is actually super something is coming from Bose-Einstein condensation, but it's very similar to the case of superconductivity. And but the major difference is that in superconducting helium, superfluid helium, you have each pairs more or less touching with each other, but independent in their space. Okay, and so this is what we usually call typical Bose-Einstein condensation case. And what is interesting is that all these new superconductors on this line has, as you can see, several pairs overlapping with each other. And this is a situation actually, something in between the typical case of Bose BCS superconductors and Bose-Einstein condensation system. So this is between these two situations. But this new superconductors are impressively similar or close to this Bose-Einstein condensation or superfluid helium. Okay, so we wanted to make it a little bit more quantitative argument. So this number of superconducting carrier or number of charge carriers divided by the mass is a property from which you can measure, or you can convert this to a typical energy scale called Fermi temperature. This is the most fundamental energy scale of the metal. And this is more showing kinetic energy of the charged particles in the metal or superconductors. So you can convert our results into this energy scale. And in the case of two-dimensional systems, this is directly related to each other. So just we need to know the damping rate and crystal structure, and you can get this property very easily. And there are some three-dimensional systems And it is very well known that this Fermi temperature or typical energy scale has a proportionality of slightly different, the carrier density to the 2 divided by the mass. But you can combine with some other experimental results and again obtain this typical energy scale, what we call Fermi temperature. And it is mostly coming from, again, our damping rate of mu-SR results. So by getting the mu-SR results, you can calculate, you can convert the horizontal axis to this typical energy scale of superconductors or metals. So this is the plot that we obtained by doing that conversion. Again, this horizontal axis is coming from the damping rate, and that is representing the number of superconducting carriers divided by the mass. And we plot TC. And these are the new superconductors that I showed you. This green one is high TC cuprates, and but we also included here in this plot the this alkali doped carbon 60, or there are some interesting materials called heavy fermions, uranium compounds, and these are the new superconductors. And compared to that, the simple metal BCS superconductors is plotted here. Okay, so this is the line that I showed you in the previous plot. So these are the BCS superconductors. So you see BCS superconductors have very high Fermi temperature, high charge energy scale, but transition temperature for superconductivity is low. Compared to that, these new superconductors have very small, rather small Fermi temperature, but very high transition temperature. The ratio is very different from these BCS superconductors. So this is again showing that these new systems are probably fundamentally different from these old systems. And as I mentioned, in the case of BCS superconductor, we would not expect TC being related to this Fermi energy. And actually, you are seeing that these three different simple metals, zinc, aluminum, and tin, they have about the same Fermi temperature, but superconducting TC is so different. And so that is the case you expect for BCS. So the new superconductors, these two parameters are related, and that's why you see this linear line. And so these are the very different feature. Okay. And the next thing you can try by making this kind of plot is that there's another important phenomena in this super something in solid state physics called Bose-Einstein condensation. All this super something phenomena is actually originating from various different types of this Bose-Einstein condensation. And so we essentially obtain the number of carriers divided by the mass. And we can assume that these number of carriers are essentially fermion particles, but then you can pair each fermions and assume that the pairing occurs at very, very high temperature. So the system is just forming gas of bosons, these paired objects or preformed pairs. And then you can ask, what would be this Bose condensation temperature? And this red dotted line is that hypothetical idealized Bose gas condensation temperature. And what we are talking about here is that, okay, so each elementary particle or each particle, either fermions or bosons, would have something called thermal wavelength, which is determined by approximate size of the particle determined by quantum mechanical feature. And at very high temperature, the high temperature means that this thermal wavelength is short. And so the particle is like a classical particle. They are separated with each other in the gas. But if you cool down from very high temperature, you will come to the temperature where the thermal wavelength becomes comparable to the interparticle distance. And if the particle is boson, then Bose gas, then these bosons would have a tendency to make special coherence of the wave function, and that is called Bose-Einstein condensation. And this Bose-Einstein condensation should have happened here. Okay. So for this hypothetical idealized situation. So compared to this hypothetical Bose condensation, the real TC of these transition temperature of these new superconductors are reduced, and they are reduced by about factor of 4 or 5. Okay, but interestingly, in some sense, it's only 4 or 5. So this again, this dotted line is parallel to this idealized Bose-Einstein condensation line. And so this is suggesting already for us that Bose-Einstein condensation may be a very important key concept to understand these new superconductors. Okay. So the third difference has been coming from, as I mentioned, the observation of Nernst effect. And Nernst effect is a kind of thermal measurement to measure the motion of this superconducting like vortex. And so it is usually expected to happen only in the superconducting state. But in some of the cuprate superconductors, copper oxide superconductors, researchers in Princeton found that this is, okay, this TC line is this one. And about this interesting effect, superconducting Reich effect occurs about 4 or 5 times higher temperature especially in something called underdoped region, in the region that the TC is increasing with charge doping. You're seeing that this Nernst effect shows up about at a very high temperature. So this is still the region that material is not completely superconducting, but something like that shows up in this high temperature. And that is found also show in diamagnetism. Diamagnetism is sort of expulsion, small expulsion of the external magnetic field that is again reminiscent of real superconductivity effect. And that happens at rather high temperature in the normal state above the transition temperature. So this is something not expected in a standard superconductivity theory of Baldwin, Cooper, and Schrieffer. And this is new. Okay, so what I recently noticed is that you can plot this onset temperature of this Nernst effect or small diamagnetism, and as a function of Fermi temperature, this charge energy scale can be measured by μSR, and but this onset temperature of the Nernst effect can be measured by Nernst effect. So you can plot the onset of this temperature, not transition real 3C, but the onset temperature of the Nernst effect in this plot. And if you do that, this data for the lanthanum strontium copper oxide comes, this circle is showing that Nernst effect onset. So this is the Nernst effect onset. You see, it's about 4 times higher than TC. So the TC is here, and so it's 4 times higher, and it's here. And there's another system called YBCO, and the point comes here. There are some 2-dimensional organic superconductor called BEDT family, and their onset of Nernst temperature, Nernst effect comes in some of the materials comes here. And in some of heavy fermions, you see also Nernst onset is here. So this Nernst effect seemingly is giving the actual some physics phenomena that corresponds to our hypothetical line, dotted line, where we expect this Bose condensation to happen if you have the already formed, if pairs are already formed at even higher temperature than this. So that means that this dotted line is not only hypothetical, theoretical line, but there may be some real observed phenomena coming on this line. Even more newer and more interesting effect is that this Hamburg researchers in Germany about 10 years ago found that if you excite the system by laser, so this red one is infrared laser, and that would make excitation of the superconductors. And then you can measure some optical property by a second laser right or probe pulse, and that is shown here by blue line. And what this kind of optical measurement can do is to find something called optical conductivity as a function of this energy of this incident and outgoing light. And this is allowing to measure something called optical conductivity. And this equilibrium result shows that the something you measure without this red laser excitation. And so in a usual superconductor, what you would see by doing this kind of optical conductivity experiment is that this in the normal state, so without superconductivity at high temperature state, you will see this red response. And this sort of peaking at low energy is called Drude-like response. And this is typical of metallic material. But if you go into superconducting state, then this Drude-like region is converted into a supercurrent. And that means delta function at a very large value at zero frequency. And so this shaded region would disappear. This is called missing Drude, or this is a signature of superconductivity in the optical measurement. Okay, so what is surprising discovery of this Cavalieri group in Germany is that if they excite the system by light, this phenomena happens at very high temperature. The superconducting like response can be observed, for example, at 100 Kelvin. This is 5 times higher than the actual known equilibrium transition temperature of this potassium 360. But they still see something very similar response as this superconducting response with this missing Drude region. And so then this Drude spectral weight is actually the same as what we are observing by this damping rate n over m star. And this is again tells us about n over m star of the superconductivity. And so from this Germany experiment, we can get transient superconducting density versus transient TC. And if you plot that transient response with this light excitation, that is shown by the circle symbol in this graph. So this buckyball superconductor, without this light excitation, it will give our point here. But with this light excitation, the point will come here on this dotted line. And the same thing was measured also in the cupret superconductor. So this is the case of cupret. And as we will show you, after we found this correspondence, then I encouraged Cavalieri to measure this organic BEDT superconductor, and they indeed found this transient-like superconductivity to start on this line, dotted line. Okay. And so the fourth element that I argued is that there is something called pseudo gap behavior, and observed again. This is somehow different from BCS superconductor. So in the cupret system, this is the phase diagram of the cupret, and if one measures the night shifter magnetic susceptibility, that shows reduction from very high temperature, not that superconducting temperature, but from very high temperature. And that is not expected in BCS. In the BCS, you would expect the reduction only in the superconducting state. So this is a signature that in this cupret systems, especially in this region of underdoped, which is TC increases with charge doping, the pairing of the fermions, pairing of charges start at rather high temperature, much higher than the real TC, and it is occurring at this and this point that pairing seems to be happening is called T star, and this is a result from magnetic measurement, but also in the conductivity measurement, the same T star was found. This is much above TC, and actually it is found in the C-axis conductivity and AB plane conductivity, and that is again can be interpreted as a result of the formation of the pair. Okay, so this is meaning that in this new type of superconductor, cuplet superconductor, this formation of the pair seemingly happening at very high temperature. Okay, so all these things would fit to the concept of Bose-Einstein condensation to BCS condensation crossover. So the newer superconductor seems to be having the pair. So pair means that the fermions, two fermions charges pair to one boson, and that happening at very high temperature, much higher than the actual TC. And the BCS superconductor, the old type of simple metal superconductor, on the other hand, this formation of the pair and the superconductivity takes place at the same temperature, nearly the same temperature. So the normal state in the case of BCS superconductors are all fermions, but in the case of this cuplets and newer superconductors, in the case of Bose-Einstein condensation-like systems, have mostly bosons already formed, and then condensation takes place at the lower temperature if this if your interparticle distance becomes comparable to the thermal wavelengths. Okay, so generally speaking, the T star or the pair formation phenomena, and also the observation of our TC versus superfluid density and so on, can be sort of mapped to this conceptual evolution of Bose-Einstein to BCS condensation crossover. And so this is most likely the essential element of the new superconductors. And we were actually claiming that or mentioning that since very early time. Okay, but one still missing kind of information is that this is not simple Bose condensation in the new materials, because the condensation or the superconductivity doesn't happen at this red dotted line. But in these new superconductors, the actual superconductivity seems to be happening in this, about 4 or 5 lower line. But as I mentioned, there are two already measured phenomena, which is transient or dynamic Nernst response, that they are showing up in this red line. So we would like to understand what is the factor that is reducing actual TC from this red dotted line. And so I would skip many slides because of the time. Please allow me to do that. But yeah, so why TC is reduced in these new superconductors from this idealized Bose gas argument. And to understand that, we can resort to analogy. And analogy can be made with this superfluid helium, because if you look at carefully, the superfluid helium, this idealized Bose gas condensation should have happened in 3.2 Kelvin, but actual TC, the actual superfluid transition of the helium would happen only at 2.2 Kelvin. So this is about 50% reduced. And as I mentioned, the cuplets, the actual TC is reduced from this idealized Bose gas line by a factor of 5. Okay, so this is, although the magnitude is different, maybe similar phenomena. And actually, this Bose-Einstein to BCS crossover has been studied afterwards very well by this something called cold atoms. And in their plot, Bose-Einstein condensation takes place at this just idealized theoretical value in the case of cold atoms, but it is reduced by factor of 4 in this cuplet superconductors. And in my opinion, this is because in the cuplet superconductors, there is a competing order. These cuplet systems are always competing with antiferrometric order. And on the other hand, cold atoms are so dilute that you don't have to compete with anything, and then this simple theoretical things work. Okay, so the way to show you that this competition with magnetic phase is important is to remember that for a given superfluid density, this, for example, this 2-1-4 system is showing lower TC than the 1-2-3 system. And the difference is that it is known that this 2-1-4 system is closer to magnetic order. And actually, let me skip this thing. So, so the effect of this competing state can be seen actually by performing neutron scattering experiment, or by noticing that in all these newer superconductors, there's some excitation, inelastic excitation measured by neutron scattering called magnetic resonance mode. And that magnetic resonance mode is related to TC linearly. Okay, and so it seems that this excitation mode is important for determining the superconducting transition temperature of this unconventional cuplet, the other systems. It's not only cuplet, but as you can see, universally, this relationship is holding. And then we can also remember the analogy with superfluid helium. You know, in the case of superfluid helium, there's some similar inelastic excitation called rotons. And roton excitation is lower in energy. And this excitation is the origin that 3.2 Kelvin is reduced to 2.2 Kelvin in the case of helium. And you can control TC of helium by changing pressure. And then you can see that TC or lambda point of the superfluid helium is proportional to this energy of rotons. So it seems that in both cases of superfluid and high TC superconductors, TC is also related to the closeness, to the somehow to the excitation of the competing order, because this magnetic resonance mode appears in the periodicity of competing magnetic order, and roton appears in the periodicity of, superfluid helium is competing with solidification of helium, and solid helium has hexagonal close-packed solid, and this is the energy. This is related to the competing energy order. And if you look at this free energy-like argument, then free energy of superconducting state or superfluid state is lower than the competing state of either antiferrometric order or this solid order of helium. And but because the superfluidity or superconductivity wins in the free energy, then you have the superconducting state or superfluid state. But their thermodynamic existence of this competing state appears in this inelastic excitation, and that controls the TC and controls the TC in this way. So closeness to the competing order is a very important factor. And in fact, if you make this phase diagram of these superconductors, this is also the phase diagram of superfluid helium. These are all separated by first order transition. And that is something you expect if you have competition between two ordering. This is a magnetic order versus superconducting order, or solid order versus superfluid order. Okay, so I think I should skip this thing. So finally, so this means that magnetic resonance mode or this competing order is very important. And finally, let me speculate that why this photo excitation in Hamburg could change TC, or it could show some transient superconductivity-like behavior. And okay, so ideally, if we could measure this magnetic resonance mode with the laser excitation, then we can see how this magnetic order was either altered, or what was done to the magnetic ordering tendency in the case of laser excitation. But unfortunately, that is technically not possible. But in this optical response, there is one response, which is this 400 Kaiser response, that is hopefully mimicking the response of magnetic resonance mode, because this is shown by one researcher that these two intensities behave almost identical in temperature variation. So if you just look at this 400 Kaiser mode, then after laser excitation, this mode is lowered in energy, and finally it comes back with 25 picosecond or some transient time scale. And during the transient time scale, this this original 400 Kaiser mode was suppressed, and the intensity is changed to the lower lower energy region. And this is very same as this is what laser is doing. But without laser, the temperature can do the same thing. And so at low temperature, you have this 400 Kaiser mode. But at high temperature, that 400 Kaiser mode disappears and gets to the lower energy. So, so this can be maybe thought that 400 Kaiser mode and the resonance mode is more or less coming from the same thing. And the laser is removing the effect of this competing order, and so removing this 400 Kaiser response. And this means that the laser is removing the magnetic order tendency, and then that is promoting, because it's killing the competitor, and that's promoting the superconducting order. Okay, so so this is my way of interpreting this why transient superconductivity can happen, because I think the laser is killing the tendency of competing order. And this is actually possibly very important, because very recently this group of Hamburg developed a new and stronger way of excitation. This red light has now comes with a longer pulse. And surprisingly, what they observed is that this transient superconducting state becomes long-lived. It used to be in the previous graph that was 20 picoseconds or something, but now they are successful in maintaining it to 1 nanosecond or 5 nanoseconds or so on. And they initially observed with this light excitation second laser pulse, but this transient superconductivity, they now can measure with this transport, just like a resistivity measurement, and show that resistivity is nearly 0 for even 5 nanoseconds after the pulse excitation. So this is showing that that this laser excitation may be really making systems to be superconducting. Okay, so finally, I will show you that I showed this graph from the beginning, and there are many materials that show superconductivity. And this one of the families in something called transition metal dichalcongenide. And this is the experiment that Zurav Guguchia has been leading in collaboration with our group. And he came to Columbia, and so he he noticed that this material is very important, and so he measured TC for series of these materials and found that it is actually showing also similar but interesting correlation between TC and this Fermi temperature. And so this is something we wish to understand soon. And most recent new material is bilayer graphene, and you put the bilayer graphene, the point comes here. And so it seems that all these new superconductors are following new principle, different from BCS simple matter superconductivity. And I hope that, I'm sorry that I'm a little bit overtimed, but the experiment and phenomenology, and especially the thinking of analogy, shows or guides us to hopefully newer understanding and higher TC with respect to this laser light excitation. So maybe I should stop here. And I'm sorry for the overtime.
Thank you very much, Momo. It was, I think everyone enjoyed your talk. The time is not a really problem. Thank you very much. And there are two questions. Maybe I'll start with one of them. So the question is, what explains the dependence of TC of a copper-based compounds on oxygen content? So why when you change the oxygen, the TC changes, follows the dome kind of shape?
Yeah, so oxygen content, actually there are various ways to change chemical, essentially doped charges by changing chemical composition. The initial doping was performed by lanthanum, strontium, lanthanum and strontium composition change, and copper 04. And lanthanum has a tendency to become 3 plus, and the strontium has a tendency to become 2 plus. And so this ionic tendency is different, and it's so the slightly different composition would change the charge carrier numbers. The oxygen has the tendency, as you probably know, oxygen has 2 minus, and putting slightly different amount of oxygen means that you can again change because of this 2 minus. You know, you have to write a chemical formula and count charge balance, and then if the charge balance is not 0, then that means your material is charge doped. And so changing oxygen concentration means that you can change the charge carrier density or carrier number, and that is actually, in my experiment, we are showing that charge number is controlling TC.
Yeah, so it's predominantly because of the doping effects and changing superfluid density. Then there's a comment. So the question was from Temuri Dogonadze. Now the comment is from Zurab Shermadini, who is thanking you very much. So he enjoyed your talk, and he was he wants to thank you a lot for your presentation. And the third one, so everyone is basically interested in the routes to achieve, room temperature superconductor, right? To get higher TC. And so from your talk, what you are saying is, in fact, you have a pairing strengths already at higher temperatures, close to room temperature, but there is some competing order which does not allow you to have superconductivity at room temperature, let's say. So one of the routes is, of course, you mentioned the light induced or the laser inducing, if you can have it at microsecond or even longer length scale, right?
Yeah. So actually, I hope to show that the superconductivity is somehow determined by this parameter, number density of carrier divided by the mass. This is one factor. And the second factor is competition with competing ordering state. And so there are a few other ways to try to go to higher transition temperature. But this laser experiment is sort of giving us a very nice indication that at least light is seemingly changing the balance between competing orders. And at least laser, even just a short time, transient time, can do the change of the balance. And so if people find a clever way of changing balance, even without using lasers, but for example, using radio RF, or microwave or more easier excitation and stable over the time, then you will be able to overcome this factor of 4 barriers. And then existing superconductors are already sufficient for being room temperature superconductor.
Yes.
So how to kill the competitor is, I think, one important route towards high room temperature.
Recently, we also showed that by strain, you can increase TC of these type compounds by factor of 3.
So Zurab is working by applying uniaxial pressure. And that is one way to control this balance between two.
Let me very shortly translate the few just important the message from your talk to the just shortly in Georgian. ძალიან დიდი მადლობა ყველას ჩვენ დაისწარით მოხსენებას. თავი მესეჯი რაც პროფესორ უემურას უნდა და ეთქვათ მექანიზმთან დაკავშირებით არის ის, რომ პრინციპში ორი მთავარი ფაქტორია, რაც კრიტიკულ ტემპერატურას შეიძლება გაზარდოს. ერთი არის ეგრეთ წოდებული superfluid density, ანუ კუპერის წყვილების რაოდენობა და მეორე არის კოჰერენტობა წყვილებს შორის და ინდივიდუალურ წყვილებს შორის და არის რაღაც მესამე ფაქტორი, მაგნეტიზმი, რომელიც თქვა დაბალი დოპირების შემთხვევაში ხელს უშლის სტატიკური მაგნეტიზმი, თქვა ამ კრიტიკულ ტემპერატურას ზრდას და პრინციპში ვხედავთ, რომ ინდივიდუალური წყვილები შეიძლება ოთახის ტემპერატურაზე იყოს, მაგრამ რაღაც ხელს უშლის, იგივე თქვა მაგნეტიზმი სტატიკური, რომელიც წევს კრიტიკულ ტემპერატურას დაბლა. და ამის მიღწევა ტემპერატურის გაზა შეიძლება ან ლაზერით, ან უნიაქსიალური წნევით და ასე შემდეგ. ანუ ეს არის ასე მთავარი მიმართულება, მთავარი გზა, რასაც მეცნიერები, ასე ვთქვათ, მივსდებთ. თუ შეკითხვები არის აუდიტორიიდან, შეგიძლიათ თხოვოთ და მიკროფონს ჩავრთავ. ან თუ ვინმეს კომენტარის გაკეთება უნდა, შემიძლია მიკროფონი ჩავრთავ. კარგით, როგორც ჩანს, შეკითხვები სავარაუდოდ არ არის. So we got a comment from Georgi Japaridze. He's a professor at the Ilias State University, and he also thanks you, Tomo, for your wonderful talk. And I again really would like to thank you very much. And actually, the long-term plan that me and David have, that maybe we can make a conference in the future in Georgia, maybe after the COVID-19 pandemic is over, maybe in a year or so from now. So I would really like to see you in Georgia and some of our colleagues.
But by the way, so if you're interested, most of the content that I talked today is published in this paper, and so more technical points you can look at this paper.
Yes, and we also give this information separately to the students that will be interested. So we will get a separate contact from the students as well.
Yeah. Thank you very much, and I hope to visit Georgia sometime.
Yes, we will organize this. I will try to organize. Thank you very much, Tomo. And
thank you very much, everybody.
შემოერთებისთვის და სხვა სემინარებსაც ასე ვგეგმავთ ყოველთვიურად სხვადასხვა უნივერსიტეტებიდან. ძალიან დიდი მადლობა ყველას. Thank you very much, Tomo. So, bye-bye.